All right, so now that we know how to display information to the user, we should probably learn how to store that information. So our next topic of discussion is something called a variable. Most of you have probably heard the term variable before from math class. You might see something like, all right, well, let's do a word problem, kids. And the teacher might start off with a statement like this. Let W be the width of the rectangle. And W represents a variable in that word problem. Now, math class is a little bit different because when you have a word problem, it's set on the page. It's never going to change. The W is more like a placeholder just to simplify the math and the equations, because we have these general equations that, for example, area is equal to length times width. Well, W is the variable inside of that equation. In programming, things are a little bit different, because programs aren't set in stone. Programs change over time. As you're interacting with a program, the values of things modify. So for example, if I'm playing a video game, the score, my player's score, may modify as they go. It may go up, it may go down. That is the difference between a variable in math class, where that doesn't change, and a variable in programming class. So let's modify this a little bit. Let's think about a variable here, more like a bucket. And what can we do with buckets? Not a whole lot. We can fill it up with stuff. So maybe this bucket is going to hold some water. I don't really have a. Maybe it's going to hold some lava, because I don't have blue here for some reason. So let's say it's got some lava in here. Great. So what can we do? We can fill this bucket up with stuff. Great. We can look inside to see how much of that stuff there is there. And we could dump it out and maybe fill it with more stuff or less stuff. The point is, we can change what's in it. Maybe there's more, maybe there's less. So that's really all a bucket can do. And in a variable sense, in the world of programming, it's basically the same thing. A variable is like a bucket or a container used to hold something. In this case, it's going to hold data. More formally, a variable is a named piece of storage. It's a container that can change its contents while the program is running. So I might have a variable that has a label on it that says score. So that tells me that the score is going to go inside of this bucket. And that's all that's ever going to go in that bucket, is the score for the player, okay, or whatever the game is that we're building at that point. So there's more pieces to this puzzle, of course. Why do we need variables in the first place? Well, the first reason is interactivity. If I'm using a piece of software, whether that's Microsoft Word or whether that's a game or whatever it is, with variables, they can change based on the way that I interact with things. So every time I type, something is storing all of the text that we type. Whereas in like a video game like Angry Birds, the launch angle that you launch your bird at is a variable. If it never changed, then you would always be launching at the exact same speed and the exact same angle, and the game would be boring. It wouldn't even be interactive at that point. So the idea of variables allows us to make our programs interactive. The second reason is readability. Our programs become easier to read if we understand what the values represent. If I see like the number 3.14 in a program, your first thought is, oh, that's pi. But do you know for sure? You don't. You're assuming that it's pi because you recognize the number, but there's no guarantee. So what we can do is we can use variables as kind of like placeholders, kind of like the let W be the width. W always represents the width for the rest of that question. If I created a variable called pi, whenever I see that, I know that that is pi. So it makes it a lot easier to understand. I don't have to think about it and wonder, is it? Is it really? And a secondary point to this is, whenever we're writing our programs, if we have a value in our program that has meaning behind it, that's what we call a magic value. So for example, that 3.14, that has meaning behind it. That represents pi. And so because of that, we want to give it a name. So anytime that you see a number in your program, it should be replaced with a variable of some kind, a name, so we know what it actually represents. Now, there are some exceptions to the rule. So for example, if I see a formula like this, let's say area is equal to 1/2 times base times height. Well, base and height are variables, and so is area. But what about the 1/2? What does it represent? It's just part of the equation. It's a coefficient. It's a multiplier. Now, in this case, it doesn't really represent anything specific, so we're not going to touch that. In this case, we just leave it alone because there's no point. You're not gaining anything by replacing it. Whereas base and height and area all have meaning behind them. So we would replace those with specific values. Even if I know the value, let's say I know in my question, whatever problem that I'm doing, that height is always a value of 5.2. I still would not do that because I don't know what that really represents. And not only that, it limits me. That means if I ever want to use this equation again, I always have to have a height of 5.2. We don't want that. So why do we need variables? Two reasons. Number one, interactivity. Number two, readability. Make our programs easier to read. So let's go back to that idea of the analogy of a bucket, okay? And let me just kind of clear the screen off here. All right, so back to where we were. Now, there are three parts to every single variable in a program. The first part is something called a data type. This basically represents what is allowed to be stored in this container, right? In our bucket analogy, it's kind of like the shape and the size and maybe even the material of the bucket. So for example, if I had a plastic bucket, I'm not going to store acid in it because that acid is going to eat right through it. I'm probably going to need a metal bucket. Okay, so these containers, the size and the shape, kind of dictate what we can store in there. In the world of programming and computer hardware, that really kind of represents how much memory it's taking up. So the next piece of the puzzle, so that's piece number one, data type. And then the next one is the identifier. So you can think of this as like the name of our variable. It's the label that goes on the outside of the bucket to inform people what is inside. So it might be something like, in our previous example, it said score. Score, so we know that score was going to be in there. Maybe in this one over here, I might have the user's name. So I might put something like username. So now I know whatever goes in this bucket, it is going to be the user's name. I don't know what the user's name is going to be, but I know that's what it's going to represent. So there is a third part to this puzzle. And the final piece is the value itself. Now this value, whatever the value is, must match the type of data. So for example, if I'm storing a username, that seems to be a piece of text. I probably don't want to be storing numbers in there. That doesn't really make sense. And vice versa, if I have a bucket that's meant to store numbers, I probably can't store text in it. That's going to break things. So maybe the value I'm going to store in this bucket is the value Daniel. Daniel is our username. Great. So these are the three pieces of the puzzle. In order to actually create a variable, I need the first two pieces. The value I can decide later on. But for now, just to get started, I need to know at least the data type and the identifier. Well, let's dig into that idea of data type a little bit further. Okay. So a data type represents a grouping or a type of information. In Java, there are two groups of data types. There is what we call primitive data types. These are basically just data, the bucket itself. And then there's also non-primitive. These ones, they do a little bit more. They're a little bit heavy-handed. We'll come back to that in a second. So let's start off with the primitive data types. These are just basic buckets. They do nothing more than hold information, allow us to look at that information, and allow us to retrieve that information. That is it. That is absolutely it. Okay. So there are a couple groupings of primitive types. So in terms of our primitives, we have two groupings. We have number types, and we have non-number types. Surprise, surprise. So let's go up here. What's our first number type? So the first number type we have to work with is something called an integer. Now you should know what an integer is from math class. In Java, we just use the word int, like that, short for integer. Now this is, just like math, it is a positive or negative number, but it has to be a whole number. Let me just kind of put an arrow there so we clarify that. It has to be a positive or negative whole number. That's great. It does actually have a range too. The range is approximately, I say approximately, negative 2 billion to positive 2 billion. Again, approximately. Let me just make this a little bit bigger. And these guys take up exactly every single int that you store, every int bucket you create is going to require 32 bits of space in RAM. Great. So what kind of numbers are we talking about? So this might be something like 7. 7's a perfectly valid integer. 213, perfectly valid integer. -42, perfectly valid integer. And 7.4, no, that doesn't work because it has to be a whole number, right? If I chose a number that's outside of the range, -2 billion, +2 billion, that will also fail as well. I have to stay within my range. So integer is the first type that we work with. The next numeric type we work with is something called a float. In Java, we use float with a little f. Now this is a little bit different. This too can be a positive or a negative number, but this time we're allowed decimal numbers. Ooh. So that gives us a little bit more flexibility. Again, these guys are 32 bits. Let me just pause. These are also 32 bits. Now, their range is pretty big. It's pretty similar to an integer. I'm not going to get into that, but one thing I do want to point out is these are meant to hold decimal places and smaller decimal values versus larger ones. So they are accurate up to about 6 to 7 decimal places. Yes, about 6 or 7 decimal places. So that's pretty good. So something like pi to 5 decimal places or 6 decimal places would be pretty reasonable. But once you start to get up to a larger amount, float's not the one we want to go with anymore. After that, we're going to use something called a double, or double with a little d. This is it's like the middle ground between a float and an integer. It does positive or negative decimal values. This one takes 64 bits of space. Sorry about that. So as I was saying, double values take up 64 bits of space, which is of course double the amount of space that a float requires, hence the name double. Now, why does it take this much space? Why do we need this? Because it can do a lot more precision. The actual range of values of a double is astronomically larger than a float, but the accuracy of it is quite a bit better as well. So these ones are actually accurate. These are accurate up to about 15 decimal places. That's pretty good for most circumstances. So when would you use a float over a double? So when you need really high precision, so things like financial software, architecture, engineering, stuff like that, that is definitely where you're going to use a double. When we're building games, those kinds of things, we're usually going to go to a float because it takes up less memory, which is very important when we're making games, but it still allows us to be pretty precise. So for most of our programs for this semester, you're okay working with double for pretty much everything until we get to the gaming side of things. Then you're going to want to switch gears over to the floats, and that's going to make your life a little bit easier. It's going to require less memory to actually track. Okay. Now, I didn't put any examples here because I wanted to show something first. So when we talk about creating an example of a double, this could be any decimal value that is positive or negative within a ridiculous range, numbers that you can't even think of. But anyways, let's say something like this. It might be something like -3.1275. That's a perfectly valid double. So is 612.2 or 0.3. So is 0. Those are valid numbers. Now, it wouldn't actually get stored as 0. It would actually get stored as 0.0. That's just the way doubles are. Now, why did I show you doubles before floats? Well, because floats are a little bit different. When we define a float, we actually have to use a special character so it knows the difference, so the compiler knows the difference between doubles and floats. Because a decimal is a decimal, right? So if I write something like the same one we have down here, the 612.3, well, if I just wrote that, it's going to think it's a double. So it's going to try and stuff 64 bits of data inside of a 32-bit container. Well, you can't fit a square peg in a round hole. It doesn't fit. So it would actually fail. So in this case, we have to tell the compiler that this is a float. We do that just with a little f. And that gives it the information that it needs to know. It says, oh, we'll only use 32 bits of space for this one, please. Now, these variables, numeric variable types, are very interesting in the fact that They are a little bit interchangeable, but not completely. What I mean by that is you can store any smaller variable types in larger variable types when they're numbers. So let me just kind of draw you a picture. So for example, if we're going down this direction, I can store an int inside of a float and an int inside of a double without a problem. It's going to fit. And we know it can handle the decimal places without a problem. And I can put a float inside of a double, although if I do that, there is some wonky things that happen with the compiler, and our decimal places may get a little bit messed up. So typically we don't do that, but it is possible. You cannot go the other way at all, ever, because first of all, a double is too big to fit inside of a float. Doesn't work. A float, it has decimals, which an integer can't handle. Doesn't work. Square peg, round hole. Is there a way though? Yes, there is a way that we can force it with some sacrifices. So we can't do it yet, but we will learn how. When you are doing this act of putting a smaller number inside of a larger number type, this is what we call implicit conversion. It means that it will automatically convert one data type into the next data type without losing any precision and without us having to do any extra work. It will just automatically happen for us. No big deal. That's what we call implicit conversion. All right, so those are our number types. What about the non-number types? There are two non-number types that we are going to work with. Oops. There we go. So the first one is called a Boolean. Boolean. But in Java, we just write Boolean with a little b. This is a very basic container. This one simply holds one of two values, either true or false. The purpose of a Boolean variable is to hold the answer to a question. So for example, it might be, is the player's age greater than 16? If so, do something different. Is the player's score better than the old high score? If so, replace it to be the new high score. So we're asking a question, and this variable will hold the result of that question, true or false. Sorry about that, it's the bell. Now, what we want to do is we're going to use this later on in the course. We're not going to use it too much right now, but we have to understand that it does exist. And the final primitive data type that is a non-number type is something called a char. Char is short for character. Okay? In Java, we just use char with a little c. And this is a single character of text. Now, when we learned how to do our print line and print commands, we learned that anything inside of double quotes, let's say ABC, that is considered text. So is something like this, also considered text. We know that it is text because it uses those double quotes. However, a char is a single character, and it can't hold more than one, obviously, but we also have to tell the compiler the difference between a char and this big version of text. So the way we do that is we use single quotes. So it might be something like this. That is a char of the letter A, which is not the same as this. That is full text for the letter A. So they're not stored the same. They don't take the same amount of memory or anything like that. They're completely different. You can't compare them directly in any way. They're not the same thing. So we have to keep this in mind. So whenever we want to talk about a single character, we use the single quotes, and we use the char variable type. So what we have so far, ladies and gentlemen, is all of the primitive data types. But now we want to get into the non-primitive. Sorry, lots of interruptions. So the last piece of the puzzle is, or the last data type we want to talk about, the last data type grouping we want to talk about are the non-primitive types. They are quite a bit different than the primitive types. Here's the difference. Primitive types, just a bucket. That's it. Non-primitive types are what we call objects. They're special. An object is a very special term in programming. What an object basically boils down to is a programming element that's made up of two things, data and functionality. More formally, we call data attributes, and functionality we call behaviors. We've been calling them methods since the very beginning. So print line, print, those are methods owned by the system.out object. Okay. Now in Java, we can create, or there's already non-primitive object types out there. For example, the one we're going to talk about is something called a string. Why do we care about this? Why is it an object? Why is it not just a primitive type? And the reason being is that these objects, they can have behaviors. They can also have data. What that means is when we store a variable, when we create a variable of this type, that means there's extra functionality built into it for free. There's also extra data that we can analyze just by storing our value in there. And this is going to make it a much more powerful tool. So the only non-primitive type we're going to focus on right now is something called a string. Now, string is text. Oh, that's what this is. That's what a string is. So we've been calling it text the entire time, but the formal name for it is string. And where it gets its name from is, it's kind of actually interesting. If you think about an analogy like this, you've been to a party before, and you've seen these kind of signs that hang up in the doorway. We have a doorway over here like this or something like that, and we have like the HAPPY, and then the happy birthday. And there's this kind of string that basically attaches all these letters together. And it keeps going and finishes doing the happy birthday. Now, why do we have this analogy? Because if you think about it, this is exactly the way a string works. A string is a collection of individual characters that have a specific order. And we can't change that order because the string is holding them all together, just like that. Now, each one of these characters has an address, hence the order. So, for example, the first character in any string has the address 0. Second one has the address 1, and then 2, 3, and then that's a terrible 3. Sorry, I'm doing this with a mouse. There we go, it's a little bit better. And then we have a 4. So this one has 5 characters in total that are numbered or located from 0 through 4. So this is what they call their address. Let's use the text here. So this is what's called an address. Another term we use for it is index. So I might say something like, hey, what character is at index 3? And you would tell me it's P. If I say what character is at index 1, you would tell me it's an A. If I say what character is at the first index, well, that's a relative term. So the first index is actually H. It's the 0 index. Okay? So this is a string. And we define these strings, or we set these strings up by using the double quotes. And that's how we know the difference between a string and a char. Now, a string, as I said, is a non-primitive type, which means it has a whole bunch of extra functionality built into it that we can use. We can cut it up, we can break it up, we can create new strings from it. We can also test certain data about it. So, for example, I can test the length of that string. In this case, it would tell me the length is 5 because there are 5 total characters. So a string is a very useful tool. Now remember, just like before, anything inside a set of quotes is going to be considered a string. So anything inside of there. So it might be something like Bob, or it might be something like 17, which is really just going to be 17. Or it might be something like this, 555 Autumn Hill, which is the address of the school. You can see that one is a combination. Or it could be something like this, score plus, let's say, 100. So what is that? Remember how concatenation works. It's going to take this piece of text, this string, and it's going to add this number, but it's going to treat that number like a string too. So we're actually going to end up with a final string that's quote, score, colon, space, 100, end quote. So it's actually going to combine those into one string. So these are all the types we have to work with. We have all of these numeric types, all these non-numeric types. These are our primitives. Then our one non-primitive we know of for now is the string data type. Now you're actually going to get to learn how to create your own objects come grade 12. We're just not there yet. Are there any other non-primitive data types? Well, yes, there actually is. Integer, float, and double actually have their own non-primitive version. We're going to stay away from those for this semester because they're going to complicate things a little bit too much for us. So we're going to try and avoid those right now. So for now, whenever you're creating an int, a float, or a double, make sure you're using the lowercase version of these. We know that string is special because it's the only one that starts with a capital letter. That tells us that, hey, this one's a little different. This is the non-primitive version. Okay, so let's move on. Let's do, let's go on to the identifier. So we talked about the data type. Now we got to get into this identifier piece. Let me just clear a little bit of my screen here. All right, so the next piece is the identifier, or the name of a variable. So when we're talking about this, we need to follow a few rules and a few conventions. Rules means if you break this rule, it will not compile in the program and it will be a syntax error. If you break a convention, it won't break the compiler, but it breaks all of the stylistic things that we're trying to do. It reduces readability, and you'll end up losing marks from me. Or if it were your boss, they may reprimand you in some way or put you back on path, depending on how serious of a person they are. But for the most part, we got to follow the rules, and we do our best to follow the conventions. Okay, so let's start off with the rules. The first rule of any variable name is that it has to be unique. You can't have two variables in the same section of code that have the same name. So I can't have two variables named score. It wouldn't work. I could have score player 1 and score player 2. That would make sense. Or I could have high score and current score. That would make sense as well. So not only does it have to be unique, you can't have multiple variables with the same name, you also can't use any of the pre-existing Java keywords. They're built in, they're set in stone, you can't modify those. You can't play with them. All right, so you have to come up with something new. The next piece of that puzzle that is a rule is it has to be alphanumeric. So letters and numbers only. However, it can't start with a number. All right, so you can have player 1, but you can't have one player. It can't contain any spaces or any special characters. So no dollar signs, no @ signs, or anything like that. Technically speaking, it can contain underscores. However, that is considered bad style at this point. We're going to be reserving underscores for something later on. So don't use underscores for now. So right now, just letters and numbers, and then you'll be safe. Okay? All right, so that's it for the rules. Be unique and use alphanumeric. Okay. Now what about the conventions? The conventions are these things that we strive for and we really, really want to stick to. So the first thing is the name should be short, concise, and descriptive. So try to keep it between 1 and 3 words. The next thing is it needs to be clear, so you don't need any extra verbiage or anything like that. So you wouldn't say area of rectangle. That's too much. You might just say rectangle area, or even better, rec area. Acronyms are okay as long as they're common sense. Short forms are okay as long as they're common sense, especially in the context of the program itself. So short and concise. But even more important than that is the name needs to be descriptive of the variable's purpose relative to the problem. So what do I mean by that? So for example, if I gave you a problem that looks something like this, where let's say a problem. Let's say I want you, old math problem. You got a wall, you got a ladder, and I want to ask you to calculate how much that ladder is if you know how far the base of the ladder is from the wall and you know how tall it is. Right? So you know from your math class that you would say, well, if I know this value down here, and I know this value down here, well, that's just Pythagorean theorem. A squared plus b squared is equal to c squared. Now, your first inclination is to create your variables and call them A, B, C. But the problem is that those aren't useful variable names. They're not descriptive. They're not helpful. We don't know anything about them. Those variable names are relative to the formula, not the problem. A better variable name might be something like wall height. Whereas, and over here, it might be something along the lines of ladder length, right? And down here, it might be something like grass length or ground length or something like that, okay? So we give our variables names, descriptive names relative to the problem. Okay, and something, it needs to be clear. So for example, if I was trying to define where somebody's location was, I wouldn't use the value X because that's too ambiguous. I might say something like player X, and that would be a little bit more clear. So it might be something like player X, X, like that. Now I know that that's the X position of the player. I don't have any fluff or anything like that. You notice the way that I'm writing these things with the way the capitalization works. So this is what we call camel case. We learned mixed case previously, where every single word starts with a capital letter. So mixed case was where every single word starts with a capital letter. Camel case is similar, where this one is every single word except for the first word starts with a capital letter. So I might have something like student number. That's camel case. or I might have something along the lines of player max speed. So there I have 3 words. Keep it short and concise. I know what it represents, and you'll notice that each word starts with a capital except for the first word. That's camel case. So we have our rules, and now we have our conventions. So we know how to name our variables now. We know what data types to use now. So what's next? The next step is actually creating the variables themselves. So I'm going to go over to Eclipse for a second. We're going to talk about it there. All right. So when we're talking about creating, defining, declaring our variables, think about this. There exists a Java dictionary, right? And in order for us to create these variables and give them names, we need to add them to the dictionary. Well, how do you add a new word to the dictionary? You define it. That's how any word gets added to a dictionary. So we have to define it first. Once it's been defined once, we can use it anywhere inside that same set of brackets. So there are 2 places that we can define our variables. We can define our variables up top here. So below the class line. So these are where our global variables go. So below the class line, but outside of the main method. Alternatively, we could define them inside of the main method. And they'll always be at the top of the section that they're in. So this would be the first thing that we see inside of the main method, or sorry, inside of the class. And this would be the first thing we see inside of the main method. Now, when I define a variable, I have to choose one of these locations. Typically speaking, we want our variables to be local, and here's why. When you create a variable, it's in memory, it's in RAM for the entire life of the set of brackets that it's in. So if I create a global variable, that means it's basically in RAM for the entire life of the program, consuming that space. That's not necessarily a good thing. Whereas if I create it inside of the main method, it's only taking up space while that main method is running. And once we learn how to create our own methods, we're going to be able to create local variables for those methods as well. And they'll only be in memory for those parts. You cannot use a variable outside of the set of brackets that it was created in. So for example, if I have another method down here, my method down here, I would not be able to use any variable created inside of the main method inside of here because it doesn't exist to its eyes. For as far as it's concerned, there's no such thing. Okay, so how do we actually define these variables? Well, we have to know 2 pieces of information. We need to know a data type and an identifier. So let's say I wanted to store the variable for the user's age. So I might say something like int user age. And that's it. I need to know the type and then the identifier, and I end it off with a semicolon. That is enough information. From now on, I now have access to this bucket, and I can put new things into it, and I can look at it just by using its name. And that will tell the program where to find it inside of RAM. So I can store data in it using the equal sign. Now, so I might say something like user age is equal to 17. Now, you have to understand that the equal sign in programming is not the same as it is in math class. In math class, I can write something like this. I can write x is equal to 5, or I could write 5 is equal to x. I don't know why I put semicolons there. We don't need this. Those are perfectly valid statements. And the reason being is in math class, equals means balance. The left side is equivalent to the right side. In programming, that's not what equal sign means. In programming, the equal sign is actually an action. It's saying store whatever value is on the right into the location, into the bucket on the left. In general, what we have here is the identifier is being assigned some expression. We'll come back to what expression really means in a minute, but that's what we're talking about. Some identifier is assigned some expression, and that value is then going to get stored in the bucket. And we can use that value now. So I can say something like system.out.println age, and then I concatenate the variable age. And what this does is it retrieves, user age. This retrieves the value of user age from RAM and substitutes it right here on the spot. And then it will concatenate that with the age colon space. Then it will try to print it on the screen. So we get all those pieces of the puzzle happening at once. But if I accidentally forgot to do this line, Well, that's a problem because it doesn't have a value yet. If I forget to do this line, that's a problem because user age doesn't exist. You can see that it immediately started to highlight and underline it. So all three pieces need to be done. I don't need to redefine user age ever again. I can just continue using it. So for example, down here, I could say user age is now equal to 18 because maybe they had a birthday. And I could display it again. And we would get two different displays on the screen. If I run this, we'll see 17 and 18 now. Because now it was changed partway through the program, and even though these two lines of code are 100% identical, our program flows from top to bottom, which means it set it to 17, displayed it, then set it to 18, and then displayed it again. So the term we use for the equals is assign. More simply put, it means store. Now there's a shortcut. If you know the value of your variable when you're first defining it, you can actually do that in the same statement that you're defining it in. So you could say int user age equals 17 right here, and then I wouldn't even need that line. I do them both at the same time. Now, of course, this only works if you know the starting value. We may be calculating it, we may be getting it from the user, or who knows what. So that may not be an option. So this is how we deal with local variables. Data type, identifier, and if we know it, we can assign it the value. Great. Let me just kind of write that simple. So we need our type, our identifier, oops, and we can end it right there, or we could have our type, our identifier is equal to a value, or let's say expression, because it's not necessarily just going to be a value. We'll come back to that. So this is our local variables. Now the only difference between defining a local variable and a global variable is that we need another Java keyword to make this happen. So let's say, for example, I wanted to store the user's age. So in this case, it's going to be a string, capital S. We'll say user age, user name, and we'll just set this to Bob. And we got a semicolon. Now, if I tried to use username down in here, watch what happens. I'll concatenate to our statements here. We'll say age, and then we'll say name, colon, and we'll add on username. So we're just building this big string up out of all the parts. Piece plus piece plus piece plus piece. You notice that the variables are not inside of the brackets. That's because if we put them inside the brackets, it would actually display the word user age. That's not what we want. We want the value to be stored. Now you notice the username is being given me an error. It says cannot make a static reference to the non-static field username. There's this special keyword right here, static. Your main method is, think of this like a label. You can almost think of it like kind of like a door, a person guarding a door. Only static things are allowed inside of the main method. Anything that's defined inside the main method gets that static label for free. So for example, user age down in here gets that static label for free because it's already inside. However, this is not inside. So in order to do, you create a global variable, we need to use this keyword static. Now that error goes away. And now when we run our program, we get age 17, comma, name, Bob. You're like, what happened to the second one? We didn't put that data down there. So now we have global data, we have local data. All right, almost done here. So we're going to finish off with the idea of what in the world is an expression? An expression is anything that evaluates to a result. Now that could be one of three things. That could be a literal value. So that literally means like an actual value. It might be 5, it might be true, it might be Fred, right? Any literal value, that is considered a literal. The next piece is it could be a variable. So you could store one variable inside of another variable, but it doesn't actually do that. If I have something like this, let's say I have int high score equals 100, and let's say we have another one, int score is equal to 200. Well, that score is better than the high score. So at some point, I might want to write code like this. High score is assign the value of score because score is better. Well, what actually happens here? Well, what it does is it goes to RAM. It says, what is the current value of score? Oh, it's 200. And it comes back down and it substitutes the value 200 right here on the spot. We don't have to do that. The program does it. And then it will just do the work and store the value. All right, so it's getting whatever value is currently stored in that variable and substituting it in the spot. Then it continues the functionality of that line. So we can store a variable. And then finally, we can actually do an entire equation. And that equation can be concatenation, or it could be mathematical setup. So it might be something like, maybe we're going to calculate average is equal to sum divided by 10. So sum is clearly a variable, average is clearly a variable in that statement. But before this assignment even occurs, this math occurs first. So it's going to take the current value of sum, whatever it is in RAM, divide that by 10, and then store the result into average. So we can build up entire expressions. There are 5 main mathematical operators that you need to know. There's plus, which of course means add, but it also means concatenate, just when we have text, right? Then we have minus, that one's pretty obvious. We have multiply. Now instead of the X for multiply, we use the asterisk, and the reason being is that X could actually be an X, so that's not good. So we actually have to use the symbol that you see on your keyboard typically for multiply. And then finally, we have the divide key. I should probably space these out a little bit. So this means divide. Right? There's no division key on your keyboard, so we use the slash. Basically, it's the same thing as saying, hey, this is a fraction. And then finally, the last piece of the puzzle, the last one, is this percent sign. This means modulus. Typically, we just say mod, though. And what modulus is, it's the remainder after a division. So, for example, you might have something like 10 mod 4. What does that actually equal? What does that come out to be? Well, 4 goes into 10 exactly twice. So that means that 2 times 4 is 8. So that means there's 2 left over out of the 10. So the result of this, the remainder of this, would be 2. And that would be your answer. Right? Why would I ever use that? Oh, you'll see. We're going to use it quite a bit. Alrighty. There is one last thing, and then we're done. The last thing is there is a special case of a variable called a constant. A constant is like a bucket that has a sealed lid on it. Once we put the value in that bucket, the lid gets put on and it gets welded shut. It can never be changed. So why would we ever want something like this? What's the point of a variable? The term variable means change. What's the point of a variable that can't change? Readability. So we want to get rid of all those magic values, and we want to put a value inside of something that we're going to recognize. So there is some pre-built constants that exist in Java already. There's actually one for pi, for example, and a few other ones. But a lot of times we just do this because we want to make sure that our code is readable. So instead of seeing these numbers that make no sense, we're going to use this actual variable, this constant variable. So defining a constant is the same as defining a variable with a couple small differences. First up, it's always going to be global. It doesn't have to be, but by stylistically, we want it to be global. So that means it needs that keyword static. Now, what tells the Java compiler that it is a constant? This does. The keyword final. Final means it cannot be changed. This is the end of the road, final. Now we just now we define it like we would any other variable. We need a data type. So let's say we're going to define one for pi. So let's use a float for a data type. Now we have to give it an identifier. Here's the next change. Identifiers for constants use what's called screaming case. Think when you're typing, you're texting to your friends, and you want to yell at them. Screaming case. It means we write in all caps. That's basically it. So pi. So that's going to be our constant. So, and then we separate each word with the underscore. That's how we separate word to word. So you might have something like acceleration of gravity, and that's multiple words. And pi is a very simplistic version. But anyways, static final float pi, all caps. And because it is a constant, we have to give it its value when we define it. So in this case, we'll say 3.14159 f. So that's pi to 5 decimal places. You can see now that it is set. It has been defined. It's bolded. They highlighted it in bold for us to let us know that, hey, this is a constant. You can't change that thing. It's stuck in stone. But now I can actually use this. Maybe I have a variable called radius, something like this. Let's say float radius. And let's set that equal to 5.2f. And we want to do float circumference. Now we know circumference is equal to 2 pi r. Well, let's do area then. We want to use we'll use this. So we have 2 multiplied by pi multiplied by radius. We just calculated the circumference of a circle. Radius is a variable, pi is a constant, and 2 is a coefficient, so we don't need any special words for that, okay, or anything. Now, the rule of thumb, as I mentioned before, is that all of our variables should be defined at the top of the section they're in. This is all commented out, so why do I have this? We can get rid of, that's fine. We'll just move this below. All of your variables should be defined before any of your actual logic, okay? Very important for organization purposes. All right, and that's pretty much it. You've seen the examples, you've seen the programs. There's tons of examples on our Google Classroom and website to work with. That's pretty much it for now. Good luck and have fun.